So let's jump into pose estimation. So when we talk about pose estimation, well, what do I mean? What is our objective? Well, our objective is we want to remotely obtain information about these objects. And maybe we want to know how fast is the object spinning, where is the center of mass, things of this nature. Maybe we can estimate the inertial matrix of the object. So when it comes to pose estimation systems, the primary two means would be the monocular camera system, or a single camera. And a single camera, we can do a lot. However, we cannot determine the scale of an object. With a single camera, we can't determine, since we have no idea of distances, and if we don't know how big an object is, we can't tell how close it is to the camera. Perhaps my hand is close to the camera, or perhaps my hand is very large. You can't tell. With a stereo camera system, we can tell, because we know the distance between the two cameras involved. We can then triangulate the distance to the object as well as sizes on the object. So we can determine scale. However, it's important to note that both a monocular camera system and a stereo camera system are unable to determine the object's mass. We simply can't estimate mass unless gravity is involved or unless we exert some sort of force on it. The only way to estimate mass is if force or acceleration is involved somehow that we know. So then where do neural networks come in? Well, the mathematics of camera triangulation are very well known and understood and well studied. And then we can map these mathematics to a neural network. So perhaps we need to perform a large number of calculations for video images very quickly. Well, neural network's good for that. Or perhaps we don't have perfect information, or we're not sure what parts of the image can be used in our equations. Neural networks are also good at that as well, because they can take the whole image data in it and analyze it all as a whole at once. So essentially, one good way to look at a neural network is it's just a function mapping. We're mapping a function, and this mapping can be trained in such a way that it's really resistant to noisy images, and perhaps even with limited variables, it can make some very good estimations. So I know you've been talking about neural networks in this course already, but since this is essentially the whole point of my talk, I really want to make sure we're on the same page. When I'm talking about a neural network, I'm talking about a convolutional neural network for the most part. And a convolutional neural network is really good for 2D information, such as an image. So you can see here we have an input layer, and then we perform a convolution on objects in that input layer. So you can see in the bottom video here, we are taking a convolutional kernel and we're convolving the kernel against the input image at different locations to output a convolved feature. And we can have a convolutional kernel designed to extract maybe a line or designed to extract a color. And then we can have a whole bunch of different convolutional filters, and some are extracting horizontal lines, some are extracting vertical lines, some are extracting colors. And we can extract all this low-level information, and then we perform another convolution, and we can extract sort of higher-level information. If perhaps two lines are near each other, maybe there's a corner. So that's sort of the idea that you can think about that's going on as we move up and up through layers of the convolutional neural network. We're gaining in complexity. We're getting more general sort of features. And hopefully by the end, you can tell about the vertex of an object, or you can tell that this is a solar panel, and then we can use this to output our pose estimation. So when we talk about pose estimation, in literature there are primarily two methods. One is the landmark method, and that's shown here. We'll take an input image, we can crop and resize the image, and then we estimate the landmark, or we regress the landmark. So you can see in the third image across the top here, there's some little green dots, and those correspond to the vertices of the object, or we've estimated the vertices, the location of the vertices of the object. And then once we have those vertices, we can correspond those with the known geometry, and we could find, well, how do we get the vertices to map the geometry? And oh, we found it. That must be the orientation. And so that's the pose estimation. Another method is the straight shot method, where we don't necessarily know the geometry, or perhaps we do and it's built into the network. And here again, we have a convolutional neural network backbone where we extract information from the images. And in this case, I think this structure is from EPFL. We output the location and we output the quaternion, or we output the attitude as well. So that's called a straight shot, where we don't necessarily have different networks performing different tasks. It's all built into one. Or we don't do a landmark to geometry matching, at least not specifically. Okay, so we've looked at the pose estimation and different ways a neural network can estimate the pose. So how does this correspond to the motion prediction? Well, if we limit our talk to simple rigid bodies, then Euler's rotational equations of motion apply relatively simply. And I'm not going to go into the derivation here because unfortunately spacecraft rigid body motion is a whole course in itself. But you can know that if you take the inertia matrix of an object, you can always find a symmetric inertia matrix for any given object. And when you do, you can derive the equations as such as this. So here we have an inertia corresponding to the x direction, the y direction, the z direction, all corresponding to a rate of revolution, omega. And we can use these to perform a quick simulation here, which I will do in MATLAB. So here we have no external torque, L. We have an initial rate of rotation with the omega here, and then we have an inertia matrix that I've selected. So I'll just quickly pull open MATLAB here. And we'll start with a symmetric case. Here we have our object. And then let's look at a case where I change one of the parameters so the object is no longer symmetric. And take a look at that. And you can see that now sort of a wobble has developed. So rigid body motion is a very well understood and very easy to model. This is something we're quite familiar with. And therefore, if we can estimate the pose over a certain number of time steps, of course we can then estimate the motion from the various poses. Okay, so once again, we can fit the observed motion to the known equations of motion. But a multi-body spacecraft would, of course, make this much more difficult. If you have two objects that aren't tethered together rigidly, what kind of the motion will then occur in that case? Or if we have fuel slosh, that's another thing that has to be modeled. So that, of course, things get much more difficult in that case. So that wraps it up for this segment. That gives us a little overview into pose estimation for spacecraft and how AI fits into that. In the next two videos, I will talk about specific case studies where we can sort of put this into practice. Thank you very much for your attention.